Hello students, today we are starting new chapter electromagnetic waves and in first assignment we have three important topics of this chapter. Though the chapter is overall very easy and very small, but these three topics are very important. Very first question is explaining the concept of displacement current. Explain Ampere's Maxwell law. Second one, write Maxwell's equations for electrodynamics. And lastly, we will discuss inductive components and radiated components of electromagnetic waves. So, three different topics in today's assignment. All the three are important. Let us start with the first one, Ampere Maxwell Law. Earlier, in chapter of magnetism, in magnetic effects of current, we saw that if we have a current carrying conductor and if we want to find out magnetic field at some point say P due to this current, what we can do is we can imagine some Amperian loop and we can use right hand thumb rule to determine direction of integration and with all that if we take closed integration e b dot dl mu 0 sigma I if we take where sigma I represents algebraic sum of all the currents within this loop. What is name of this loop? Amperian loop. So with this formula, once you have mu 0, that is permeability of vacuum known, if you can find out the total current enclosed by Amperian loop, then we can easily find out magnetic induction, magnetic field at point P. And this equation is Ampere circuital law. Okay, but then Maxwell found some discrepancy. Uh, he suggested that if we say that there is magnetic field produced because of electric current or because of electric field, the converse should also be true. And to resolve the discrepancy, he he came up with one situation where this equation could not explain the magnetic field prevailing in some region. Let us see the situation. If you consider a capacitor being charged by some external source, now we know that when you connect capacitor with some DC source, there is no current flowing through the capacitor except for few initial milliseconds, because initially the capacitor is being charged and hence as long as the charge is being deposited on the plates, you have current flowing through this wire. So at that time, if you consider some point P and then if you try to find out magnetic field at that point using Ampere circuital law, you will get a very correct answer. But at that time, what was observed was that if we consider another point Q and there if we try to find out magnetic field, this equation will not be able to help us. They could actually see magnetic field prevailing at point Q. Let me draw the diagram once again. If I consider two plates of capacitor and then what we are talking about is magnetic field at point P. Can we find out magnetic field at point P? Yes. All you have to do is imagine some Amperian loop and apply this law. B dot dl is equal to mu 0 sigma and you will be able to get the answer. But then if you look at point Q, which is between the two plates, where you have electric field, you don't have electric current, you have electric field. And what is the direction of electric field? Electric field is going from positive charge to negative charge. So between the two plates, if you place magnetic needle, it is showing some deflection, means there is some magnetic field, but that magnetic field cannot be found out by Ampere circuital law. So what to do? So at that time, if you can imagine some closed surface, we can say that the flux passing through this surface is changing. Remember, the electric flux can be given as E dot dA, isn't it? Uh, so d phi is E dot dA, and as this electric field is changing with time, we can say that flux is also changing with time. So if we find out rate of change of this flux, let me write it as area is constant, electric field is changing, so we can write it as A dot dE by dt. And what is electric field? We know that electric field is sigma by epsilon 0. What is sigma? Surface charge density. Okay, so if we express it this way, then it becomes A by epsilon 0. I am dropping vector sign because the area vector and electric field both are in the same direction, so cos theta will be 1. Okay, so no need to mention cos theta, no need to mention vector sign. And then sigma, we know that sigma is q by A. So sigma into A will give me q, or else let it be q by A, and then it will be 1 by epsilon 0 dq by dt. So essentially what we are talking about is that epsilon 0 d phi by dt, if we take, it is dq by dt. Now, though there is no actual flow of charge, this term is behaving as if it is current. Look at the dimensions of dq by dt, it is current. But this current is not due to any physical motion of any particle, and hence this term is regarded as displacement current. Or in other words, you can say that whenever flux changes in some region, the effect produced is very similar to some current passing through any conductor. What is the effect of current? It produces magnetic field. Similarly, changing flux also produces magnetic field. And hence, this equation, Ampere's law, was corrected. What is Ampere's law? That closed integration B dot dl is equal to mu 0 I. I am dropping sigma notation. We'll consider IC to be total conduction current. What do you mean by conduction current? The current which is because of flow of charges. This equation was modified and a new law was given, which is known as Ampere Maxwell Law. And what is the modification? Modification is B dot dl can be found out by mu 0 IC plus ID. So you can write it as mu 0 IC plus mu 0 epsilon 0, sorry, mu 0 epsilon 0 ID. Not ID, mu 0 epsilon 0 d phi by dt, where phi is electric flux, and let me mention it, d phi E by dt. So this is the Ampere's Maxwell law. So with this, we have actually four equations which make basis of new branch of physics called electrodynamics. What are these equations? Very important four equations of electrodynamics. We already have studied this. First one is E dot dA, that is electric flux, is sigma q by epsilon 0. So if you are talking about flux, electric flux enclosed by any charge, you can take it as a ratio of these two, charges enclosed by any surface divided by permittivity. Similarly, we have B dot dA for magnetism. If you are talking about closed surface, the magnetic flux is 0. Why magnetic flux is 0? Because we know that there is no uh, single north pole or south pole existing. Now we have B dot dl. What is B dot dl now? Ampere's Maxwell law, which says that mu 0 IC plus ID if you take, you will get closed integration of magnetic field over some line. And similarly, if you take E dot dl, it is E dot dl is actually potential, and that is minus d phi by dt. Which phi we are talking about? This is magnetic flux, and this is actually Faraday's law for electromagnetic induction. So Gauss's law for electric flux, uh, for magnetic flux, Gauss's law for magnetic flux, Ampere's Maxwell law, and Faraday's law for electromagnetic induction. These four equations are known as Maxwell's equations, and these four are considered to be as pillars of electrodynamics. So this is second question of today's assignment, and then let us move to third question. What is third question? Compare inductive components and radiated components of electromagnetic waves. The Maxwell's contribution to electrodynamics is considered as a remarkable idea when he suggested that even varying electric field can produce magnetic field. That gave rise to the concept of electromagnetic waves. So if you consider an inductor which is connected with, say, a capacitor. So which circuit we are talking about? We are talking about LC oscillator circuit. So suppose if we consider that initially capacitor is empty and then gradually it is getting positive charge on upper plate, negative charge on lower plate, then in the surrounding region at any point if you see, you will see that electric field is downward. Okay, and it is growing. Gradually it will grow. Why it should grow? Because as you deposit more and more charge, the intensity of electric field will increase. And if you go away, electric field here may be less, electric field here may be less, but the direction will be same. But then after some time, when the charges are swept, the upper plate will be negative, lower plate will be positive, and consequently the direction of electric field will also change. So whenever these charges here oscillate in the surrounding region, electric field is also changing its direction. And what if electric field is changing its direction? If electric field is changing its magnitude and direction, magnetic field should also be produced. And hence, we can say that in all this region, we have electric field varying and magnetic field is also varying along with it. And then this disturbance of electromagnetic field is called electromagnetic wave. So electric field is varying, magnetic field is produced simultaneously, and they have some relation. Wherever you have electric field, magnetic field, or magnetic field produced because of electric field, there is some relation between the two. So there are two area. This region is called region close to the source, whereas very far away from the source, if you go in distant region, the characteristics of electric field, magnetic field both are not same. And based on this characteristic, the components of electric field and magnetic field are given two different names: inductive component and radiated component. So the component of electric and magnetic field in closer region to the source are known as inductive component of electric field and magnetic field, whereas if you go far away from the source, in this case this is source, so those components are known as radiated components of electric field and magnetic field. What is the difference? Difference is in near region, if you look at the electric field and magnetic field, suppose if I describe electric field as this, See what is happening here. The electric field is falling very fast, whereas in the radiated component electric field is falling, it is decreasing its value but slowly. So here the fall is proportional to 1 by r cube, and in this case electric field is decreasing at the rate of 1 by r. So that is one difference. Second difference is, in this case if you see, the magnetic field goes like this. What does it mean? The point where you have maximum electric field, magnetic field is 0. The point where you have maximum magnetic field, electric field is 0. And the two are mutually perpendicular. So that is true with the radiated component also, but in case of radiated component, the two are moving along with, means they have zero phase difference. Exactly when you have maximum electric field, we get maximum magnetic field. So it can be said that phase difference between E and B, electric field and magnetic field, is pi by 2 in inductive component, whereas in case of radiated component, that is when you go at larger distance from the source, you will see that phase difference between electric field and magnetic field is 0. They are going up and down together. So 3 points: definition of inductive component, radiated component, first point. Secondly, how fast electric field falls in either case, and lastly, phase difference. So that is all for today's assignment. Thank you.